See, now let us derive the expression for time period of a spring mass system when the spring mass system is in horizontal plane and vertical plane. First, what do you mean by spring mass system? Means a spring which is connected to some mass capital M. This is called a spring mass system. Generally, when we say spring mass system, it means you have to assume like this. Now, the first point is when the spring mass system is in horizontal plane. That is, see, this is my horizontal plane. On this horizontal plane, there is a rigid support here. To this, I connected a spring, and to that I connected a mass. This is my mass capital M. So this is called a spring mass system, and this spring mass system is on an horizontal plane. Okay. Now if I make this to vibrate, then what will happen? This mass will oscillate to and fro. That is, it makes SHM, and it undergoes SHM with some time period. Let us derive the expression for that time period. Now see, first, now what I'll do, I'll apply a force F in this direction. When I apply a force F in this direction, what will happen? This force will extend the spring. Now already we know that if the spring is extended by some amount X, then what will happen? There will be a restoring force RF developed in the spring that will be opposite to the applied force. Then what will happen? The formula for that restoring force is R is equal to FR, RF is equal to FR, that is equal to KX. Now let us see the case. Now this is the case where there is no force on the mass. Now if I apply a force on this mass, what will happen? The same horizontal plane, this spring will extend by some amount X. Okay, by some amount X. This mass capital M. What is that amount? The amount of that extension will be this part. This will be the amount of extension. Now if you see at this case, applied force is like this, restoring force is like this. Okay, restoring force is like this. For time being, I will take it as restoring force RF. Now the formula for that restoring force is RF is equal to, I will take this as F. Why? Because both will be same. At this stage, what happened? Both are at this mass is at rest. No, that is applied force is equal to restoring force. So RF is equal to F, that is equal to KX. Now when I leave, what will happen? This mass will oscillate like this, taking this as mean position. So this as mean position. This is mean position. This will be my extreme position. Now when I leave this mass, what will happen? It will come to its mean position, move back to certain distance. That distance, if I take that position as this, then this will be my extreme position, and again it will come back. Finally what will happen? This mass will undergo SHM like this, taking this as mean position and taking these two as extreme position. Okay, so it will oscillate like this. It will undergo SHM like this. Now let us derive the time period for that SHM. The other point you have to remember is, see, that's what written here. At mean position, the acceleration is 0. So now this is extreme position. Now when this mass comes to here, we know that for a body undergoing SHM, at mean position acceleration will be 0 and velocity will be maximum. Now at mean position acceleration is 0 means force is 0. Force is 0 means it should stop at the mean position. But what happens? Because of inertia of motion, what will happen? This mass will keep on moving towards this direction. That's what written here. At mean position, its acceleration is 0, velocity is maximum, but still it continues to move because of inertia of motion. Okay, so what happens? Though force is 0 at mean position, but because of inertia of motion, what will happen? It will move like this. So when it moves like this, what will happen? See, at this position, if this mass is at a mean position, what will happen? The spring will be in unextended state. That is this position. It will be in unextended state. That is force is 0. That's what our concept says. Now, what happens if this mass, because of inertia of motion, if it moves towards this direction, what will happen? Slowly, the spring will compress. Okay. When the spring compresses, what will happen? Restoring force will be developed. And we know that this restoring force is proportional to X. that is amount of compression. So what happened, with some velocity it will start moving towards this direction. Now as it moves, that is as it reaches towards extreme position, what will happen, the value of restoring force will increase, and it reaches to a stage, that is the value of this restoring force reaches to a stage where it what you call it brings this mass to rest, that is velocity is equal to 0. Then what will happen, it will come to rest at this point. Now at this point what will happen, at this point what happens, this spring is fully compressed. Okay, then what will happen, this compressive force will again pull this mass towards this direction. That's why this mass again will move towards this direction. Okay, that's what happens. So initially this is equilibrium position. Because of restoring force created by this spring, this mass will move like this. Now here what happens, since the though the force is 0, but still it will move like this because of inertia of motion. Now when the mass starts moving like this, what will happen, this spring will slowly get compressed, that is the restoring force will increase, the restoring force will increase. Now there will be a stage where this restoring force will bring the body to rest, that is my equilibrium position. At this equilibrium position what will happen, this restoring force again will pull the mass, will push the mass in opposite direction, because of which what will happen, this mass will move like this and again go like this. It will move like this again here, because of inertia of motion again it will go like this. Now when it reaches to extreme position, restoring force will act in opposite direction, and again that restoring force will pull the mass in this direction. So finally what will happen, because of this restoring force, this mass will move to and fro about the mean position. Okay, now let us derive the expression for that time period. Okay, now see the formula for that restoring force developed, Rf is equal to minus kx, according to this logic. Now according, this restoring force is acted on a body of mass m. Okay, according to Newton law we can write the formula for that force is F is equal to ma, that is equal to minus kx. Then A can be written as A is equal to minus k by m into x. Now if you go to the standard formula of SHM, the formula for acceleration of SHM, A is equal to minus omega square x. So this is similar to this, that means this oscillation is SHM. Now if we compare these two, we'll get omega square is equal to k by m. Okay, omega square is equal to k by m. Then omega will be equal to omega, let me write here, omega is equal to root k by m. Then omega, if it is written as 2 pi n, then what will you get, 2 pi n, 2 pi by t, that is 2 pi n is equal to root k by m. Then n will be equal to, let me write here, n will be equal to, n is equal to 1 by 2 pi root k by m. We know that n is proportional to 1 by t, that is t will be equal to 2 pi root m by k. So this is the expression for time period of that spring mass system when the spring mass system is in horizontal plane. So time period t is equal to 2 pi root m by k. Okay, now let us see the case of this same spring mass system if it is in vertical plane. So as I said that spring mass system means you have to assume a spring connected to a mass, capital M. This is spring mass system. Okay, now this spring mass system is in vertical plane. So this is in vertical plane. Now the point that you have to remember is, see, let me take this spring like this. So initially my spring is like this. Now if I don't apply any force, what will happen, this spring will be in natural state, that is restoring force is equal to 0. Now to this spring I'll apply some force m, I'll apply a mass, I'll attach a mass capital M and hold this mass. Now next what will happen, when I leave this mass, what will happen, because of gravitational force this mass will come down, that is this spring will extend and this will oscillate like this, and finally it will come to a position to some equilibrium position like this. So what happened, this is unextended state of the spring because of gravitational force. this extended by an amount x. So if I take this as my natural length, that is initial length, so this will be extension. So this will be extension. The point you have to remember is, already in this case there is some some restoring force that is equal to kx. Okay, now what I'll do is I'll disturb. So this is already extended. In this case, what happens? See, if you apply free body diagram for this mass, what will happen? This is my mass. The weight of this mass, mg, will act in downward direction. Restoring force will act in upward direction, kx. So we can write kx is equal to mg. Okay. Now, so already in this situation there is some restoring force kx. Now to this, what I'll do? I'll pull this mass by some amount y in the downward direction. Then what will happen? See, this will be the case. This is my spring extended by some amount y. Capital. Let me take that extension as y. Let me extend this. So this is my amount of extension. Then I'll leave. So I'll extend this spring by some amount y, and then I'll leave. Then what will happen? This mass will oscillate like this, taking this as mean position. That's what you have to remember. Taking this as mean position. So this will be mean. That is, this position will be mean position. This will be my one extreme position, and my other extreme position will be somewhere here, such that this distance will be equal to this distance. Okay. In this case, that distance will be equal to y, which is nothing but the amount of extension. Okay. So similarly, this distance will also be equal to y. Now let us try to derive the time period of this oscillation. We came to know that it undergoes SHM. Now let us try to derive the time period of that oscillation. So that okay, time period for that oscillation. Now, if you see this case, see, at some instant, let y1 be the what you call extension of the spring. Now at that instant, the restoring force will be F is equal to minus k into x plus y1. Why? Because already in this stage there is some restoring force x, there is some restoring force kx. Now to this, see, what did I do? I took that y1 is the displacement at some instant. So to this x, the spring extended further by an amount of y1. Then the restoring force will be minus k into x plus y plus mg. Why? Because, so see, if I assume that stage, if I try to draw the free body diagram at that stage, what will happen? This is my mass m. Restoring force will be k into x plus y, x plus y1. This y1 is because of extra extension y1, and mg will be in downward direction. Then the total restoring force will be this, minus k into x plus y1 plus mg. Now according to Newton's second law, this can be written as ma is equal to minus k into x plus y1 plus mg. Already initially we came to know, we derived that the value of kx will be equal to mg. So ma will be equal to this minus kx can be written as mg, that is minus mg minus ky1 plus mg. This mg will get cancelled, that is ma is equal to minus ky1. Okay. So from this I can write a is equal to minus k by m into y1, which let me write here, which is similar to a is equal to minus omega square y. That is, it is undergoing SHM. Now if you compare this and this, we'll get omega is equal to root over k by m. If you apply omega is equal to 2 pi by n, 2 pi by t, then we'll get time period t is equal to 2 pi root m by k. Okay. So that's what here you have to remember. Time period t is equal to 2 pi root m by k, which is similar to our previous case. So the final conclusion is, if you oscillate the spring along horizontal plane, similarly if you oscillate the spring along vertical plane, the formula for time period is t is equal to 2 pi root m by k. So it doesn't change when we oscillate the spring along horizontal direction or along vertical direction. Okay, next thing is, let us see some applications regarding this. The time period of spring mass system does not depend upon acceleration due to gravity. So this is one important point. See, earlier we derived the expression for time period as t is equal to 2 pi root m by k. Okay, now see, let me show you. The expression for time period is t is equal to 2 pi root m by k. Now, and at one stage we got this expression kx is equal to mg. From this we can write k by m is equal to g by x, or m by k is equal to x by g. Okay, we can write like this. M by k is equal to, means instead of this m by k, I can substitute x by g. Okay, so let us come now. Instead of this m by k, what I can do? I can write x by g. That is equal to 2 pi root x by g. X by g. Remember that this x is the initial extension, but not the extension that we created to undergo SHM. Okay, now see. Now if you see, time period is, if you see this expression, it seems that time period depends upon g. That is 2 pi root x by g. If you see this expression, it appears that time period depends upon g. But the point is, time period of the spring mass system does not depend upon acceleration due to gravity. Now let us see. See, what did we do? This is my spring in unextended state. To this spring, what did I do? I applied, I hanged a mass, capital M, due to which it underwent an extension x. Okay. Now in this case, what will happen? Mg is equal to kx. Now here, if you observe, if g increases, what will happen? The value of x will increase, such that the value of x by g is constant. So here, what does g and x are directly proportional? That's what you see. What did he say? Time period of the spring mass system does not depend upon acceleration due to gravity. Now let us see the case where I increase g. If I increase g, what will happen? The value of x will also increase, such that the value of this x by g is constant. That is some constant here. Then this entire term will be constant. So the final conclusion is, though I change the value of g, the value of time period does not change. That is, though I change, go to some other place where g becomes g by 6, that is on moon, then what will happen? On moon also, this spring mass system will oscillate with same time period, same value of time period. Okay. Now finally, the value of time period of spring mass system depends upon mass and spring constant. That's what depends upon mass of the body attached to the spring and force constant of the spring. Okay. Now the next point is, if you see the if you observe the time period of simple pendulum, that is t is equal to 2 pi root L by g. Now in this case, the time period of spring mass, the time period of this simple pendulum depends upon g, whereas the time period of this spring does not depend upon g. Now let us assume like this. We took this simple pendulum as well as spring mass system to moon, on moon. Okay, I oscillated these two. Okay, then what happened? The time period of oscillation of spring mass system will be equal to the time period of oscillation of spring mass system on Earth. That is, time period of spring on moon will be equal to time period of spring on Earth. But in the case of simple pendulum, since time period depends upon g, then we can conclude that the time period of simple pendulum on moon, sp on moon, will not be equal to time period of simple pendulum on Earth. The reason is, the value of g on Earth is not equal to the value of g on moon. That is, since t depends upon g, so time period will change. That's what written here. When a spring mass system next, so that is the application of this. If there is no gravity, simple pendulum does not oscillate, but spring mass system can oscillate. So this is other application. What if you see this, time period is independent of g. No gravity means no g, but still spring mass system will vibrate, because there is no g term in that time period of spring mass system. But if you go to the case of simple pendulum, G factor is there. Then what will happen? In what you call no gravity space, in no gravity means no G. Then this simple pendulum will not oscillate. Will not oscillate means what does it mean? So this is my mean position. Now in order to oscillate, I'll bring this simple pendulum, this bob to extreme position. Now if since there is no gravity, that is no G, that is no T, then what will happen? It will stay at this position. It won't oscillate. That is the meaning of no oscillation. Means this bob will remain at some fixed point. There won't be any oscillations. Okay, next. When spring mass system is under equilibrium and is further stretched by a distance y and release, it executes SHM with an amplitude y. Now let me explain this. Okay, let me explain this. Now see, this is my spring which is in uncompressed state. Now to this spring I hanged a mass. Then what will happen? This will oscillate and finally it will come to some equilibrium position. That's what we discussed. Some equilibrium position, that is this spring will extend by some amount x. Okay, and it will come to rest. Now what did he say? When a spring mass system under equilibrium, now in this case this is in equilibrium, is stretched by an amount of y. Now what I'll do? I'll still stretch this by an amount of y. Then what will happen? And is released means if I stretch this by an amount y and release, what will happen? It will undergo SHM. It executes SHM with an amplitude y. That's what here you have to remember. That is, okay, it undergoes SHM. Now the value of amplitude of this SHM is nothing but your value of extension. Okay, your value of extension. That is, the amplitude will be equal to y. Now in other case, if you extend this by an amount of y1, then in that case what will happen? The value of that amplitude of oscillation will be y1. So the other point you have to remember is, so in this case, in first case the value of amplitude is y. In second case the value of amplitude is y1. Okay, so amplitudes are different, but the point you have to remember is the time period will be same. Time period t is equal to 2 pi root m by k. So time period doesn't change. Means the final conclusion is, if I extend this mass by any amount y, it may be y1, y2, y3, y1, y4, so on. The amplitude varies, but the time period will be same. Time period purely depends upon the mass hang, which is nothing but small m, and k, which is nothing but spring constant of this spring. So that is the final conclusion of this. When a spring mass system is under equilibrium and is further stretched by an amount y, then the amplitude will be equal to y, but the time period will remain same. That is, it will be similar to your previous extension. Okay, next. When a spring mass system is under equilibrium and an additional load m1 is attached, then the new time period will be. Means what does it mean? Means, see, this is my spring mass system. So if I draw like this, what does it mean? This part is completed, this part is completed. That is, already this spring is, and this mass is means already there is some restoring force F is equal to minus kx on this mass. Okay, now, so now in this case what will I do? If I oscillate, what will happen? It undergoes SHM. Means if I pull this down and leave, what will happen? It undergoes SHM with a time period t is equal to 2 pi root m by k. Okay, now in this case, if I add some more mass m1, such that total mass will be equal to m plus m1. Now in this case, after adding this mass, if I oscillate, then what happens is, now this system, that is combination of m and m1, will oscillate with a time period t is equal to 2 pi root m plus m1 by k. Okay, next. See, we already know that this, I think in previous discussion we wrote m by k as x by g. Okay, now if you apply the same logic, you can write 2 pi root x plus x1 by g, where x is the extension produced when m mass is hanged. Okay, x1 is the extension produced when m1 mass is hanged individually. Then in this case, the formula for time period will be T is equal to 2 pi root x plus x1 by g. Okay. Next term is, see, till now we didn't discuss about this mass of the spring. Generally, this is also made with some material. That means it will also have some mass. Now, if we consider this mass, that is mass of the spring, then the expression for time period will be T is equal to 2 pi root over m, which is nothing but mass hanged to the spring plus ms by 3 by k. Okay, so this is the time, this is the expression for time period of a spring mass system if the mass of the spring is considered. Now, see why we wrote here ms by 3, because for a spring, if you calculate the center of mass, it will be at 1/3 of the spring. Okay, if you calculate the center of mass of the spring, the center of mass of the spring will be at 1/3 of this spring. So we'll write, we'll add a term ms by 3 to this mass term.